Hello everyone. Today I will talk about HybridDNN, a framework for high-performance HybridDNN accelerator design and implementation. My name is Hanchen and this is a joint work from University of Illinois at Banachengping and Fudan University from China. I'm a PhD student in UIUC, advised by Prof. Deming Chen. My research interests lie in the area of hardware acceleration, high-level synthesis, and deep learning. Here is my personal website where you can find more information about me. Today, I will first talk about the motivation of this paper and a high-level overview of the HybridDNN framework. Then, I will dive into details of the accelerator design and the corresponding design space exploration. Finally, I will provide some experimental results before we conclude this presentation. Recent years, more and more applications begin to use cloud or embedded FPGAs for DNN inference. To achieve the goal of easy and fast DNN model deployment in different scenarios, we are motivated to build a complete and automated design flow which is flexible for various DNNs and FPGAs. Meanwhile, to further improve the performance and efficiency, we've seen lots of research about fast convolution algorithms, such as Winograd and FFT. Among all of these fast algorithms, Winograd has shown its strong capability of improving the efficiency of convolutional layers. This diagram briefly shows how Winograd algorithm works. It first transforms weights and input tiles into Winograd domain, where convolution operations are converted to element-wise matrix multiplication, EWMM. After the computation in the Winograd domain, the intermediate results are transformed back to the spatial domain for carrying out the final result. The pros of Winograd algorithm is it can reduce the multiplication number of convolutional layers, but it also has several cons. For example, it is not friendly to fully connected layers and 1x1 convolutional layers, which are widely used in modern DNNs. Meanwhile, it demands higher memory bandwidth than spatial convolution. These cons demonstrate the low flexibility of Winograd algorithm for various DNNs and FPGAs. To overcome these disadvantages of Winograd algorithm, we are motivated to design a hybrid spatial and Winograd architecture. However, such a hybrid architecture is facing several challenges. For the accelerator design, the spatial and Winograd convolution are supposed to reuse the same computation resource to improve the efficiency of the FPGA. Meanwhile, a hybrid architecture will bring us a much larger design space than a homogeneous one. So we need accurate modeling and efficient design space exploration to deliver the optimal solution. To tackle these challenges, we propose a HybridDNN framework with 4 steps. The input of HybridDNN framework is FPGA specification and a pre-trained DNN model. After the DNN parsing and the design space exploration in step 1 and step 2, we generate the DNN mapping strategy and the HL's template configuration. Then, in step 3, a compiler is developed to generate instructions and data files for the accelerator. Meanwhile, we leverage vendor HL's tools and FPGA design flow to generate FPGA bit stream. And finally, in step 4, the DNN application is deployed to the targeted FPGA. Now, let's take a look at the accelerator design. We propose an instruction-based accelerator with a customized instruction set. In the accelerator, a control module will load instructions from external memory and distribute them to different functional modules. There are 4 functional modules in the accelerator. The first 2 modules are load modules. They will load input feature maps and weights from external memory to on-chip buffers. Then, the compute module will carry out the computation before the save module writes back the results. All of these functional modules are dynamically scheduled into a module-level pipeline and can work concurrently to guarantee the efficiency of the on-chip resources. The most important module is the compute module, and the key component is the processing engine, PE. Most of computation resources on FPGA are allocated to this PE. It contains PT times PT gem cores and can be reused by Winograd and spatial convolution. Here, each gem core is a broadcast array paralleled along input and output channels with a factor of PI and PO. In each clock cycle, each gem core is able to carry out 1 matrix vector multiplication between a PI length vector of input feature maps and a PI times PO matrix of weights, and generate a PO length vector of output feature maps. For different convolution modes, these gem cores are organized with different patterns. For spatial convolution, all gem cores are constructed into a large broadcast array and work together. But after the Winograd transformation, the original convolutional layer is converted to PT times PT independent gem computations. So for Winograd convolution, each gem core will take care of one gem computation and work independently. To accommodate the different patterns of gem cores, we design a pair of load and save manager to reorder and manipulate the input and output data. They can switch between spatial and Winograd mode. In spatial mode, the input and output data will go through the data path for spatial convolution. And in Winograd mode, the input data will be transformed from the spatial domain to the Winograd domain in the load manager, while the output data is transformed vice versa. Because Winograd and spatial convolution are reusing the same computation resources in PE, the only resource overhead of introducing our hybrid architecture is the LUTs used for Winograd transformation in load and save managers. This hybrid accelerator design brings us a large design space to explore. For hardware parameters, we have 4 parallel factors: PI, PO, PT, and NI. And for software parameters, for each DN layer, we can select between 2 convolution modes and 2 different data flow strategies: input stationary and wait stationary. With all of these tunable parameters, the objective of DSE is the overall latency of the targeted DN model. We propose a 4-step DSE algorithm. In step 0, we construct accurate models for estimating the latency and FPGA resource utilization under different parameter combinations. Based on these estimation models, in step 1, we search for design candidates with different hardware parameters under the constraint of FPGA resources. And in step 2, we search for the optimal software parameters combination for each design candidate selected by step 1. Finally, in step 3, we walk through all of the design candidates and pick the one with the lowest latency as the finalized solution. In the experiments, we take VG16 as targeted DN model and Xilinx VU9P and PingZ1 as targeted FPGAs. After going through our hybrid DN flow, the configuration and resource utilization on these 2 platforms are shown on the right-hand side. We observe that the accelerator generated for the cloud FPGA VU9P achieves a more than 3,000 GOPS performance and the highest energy efficiency. To evaluate the flexibility of our accelerator, we map 60 and 40 different convolution layers onto VU9P and PingZ1, respectively. The kernel size of each test case is annotated to the horizontal axis, while the feature map size and channel size are represented as the yellow scope and gray bars in the chart. We can observe that spatial convolution supports all kernel sizes, and its performance is stable and close to the achievable peak performance. Winograd convolution has a much higher peak performance than spatial convolution. However, its performance is sensitive to the feature map size, because small feature maps will cause low weight reuse rate, and the performance will be bounded by memory bandwidth. On these 2 FPGA platforms, Winograd mode performs better due to the sufficient memory bandwidth. However, in the other scenarios where the available memory bandwidth is limited, spatial mode may outperform Winograd mode. The flexible support for both convolution modes allows our HybridDNN framework to fit into a wide range of different scenarios. In summary, in this paper, we propose HybridDNN framework, which can generate highly optimized accelerators for FPGAs. We propose an instruction-based hybrid architecture and an efficient algorithm for optimizing hardware and software parameters. Finally, we evaluate the performance and flexibility of our generated accelerators on both cloud and embedded FPGAs. That's all for today. Thank you.